In this example 4, we are going to compare CSTRs and PFRs. It is interesting to compare the volume of CSTRs and PFRs required for the same job. To make this comparison, we shall use the data in the figure 2.2 to learn which reactor will require the smallest volume to achieve a conversion of 80%, a CSTR or a PFR. The entire molar flow rate FA0 equal to 0.4 moles per second, and the feed conditions are the same in both cases. Solution. Let's use the table 2.3 that we use in problem number 1, number 2, and number 3. So we have two rows here. In the first row, we have the conversion x that going from 0.0 to 0.8. And in the second row, we have FA0 divided by minus RA that goes from 0.89 to 8. The CSTR volume that we obtained was 6.4 cubic meters, and for the PFR volume was 2.165 cubic meters. When we combine in the figure E2/2 and E2/3.1 on the same graph, we see that the crosshatch area above the curve is the difference in the CSTR and PFR reactor volume. For isothermal reactions greater than zero order, the CSTR volume will usually be greater than the PFR volume for the same conversion and reaction conditions, which are temperature, flow rate, etc. We see that the reason the isothermal CSTR volume is usually greater than the PFR volume is that the CSTR is always operated at the lowest reaction rate. Example, the minus RA equals 0.05 moles per cubic meter second. In figure E2 4.1b, the PFR, in the other hand, starts at a high rate at the entrance and gradually decreases to the exit rate, thereby requiring less volume because the volume is inversely proportional to the rate. So let's see these figures. And here we have the comparison of CSTR and PFR reactor sizes. But we must remember that for the CSTR, the volume was the rectangle with a height of 8 and base of 0.8, so that was 6,400 liters or 6.4 cubic meters. And for the PFR is only the area under the curve. So the crosshatch is the difference between these two reactors. That's a lot of volume of difference. We can see that the volume for a PFR is a bit less than 1/3. On the plot to the right, we see that the CSTR is always operating at the lowest rate, which is 0.05, because remember that it's perfectly mixed. Then example 5, comparing volume for CSTRs in series. For the two CSTRs in series, 40% conversion is achieved in the first reactor. What is the volume of each of the two reactors necessary to achieve 80% overall conversion of the entering species A? And we are going to use again table 2/3. Remember that we have two rows. In the first row, the conversion X, and in the second row, FA0 divided by minus RA, because remember that is all that we need to construct the Levenspiel plot, which will give us the volume of the reactors. Solution. For reactor 1, we observe from either table 2.3 or the figure E2/0.5 that when x equals 0.4, then FA0 divided by minus RA1, which is evaluated at x equals 0.4, is equal to 2.05 cubic meters. Then the volume of the first reactor will be FA0 divided by minus RA evaluated at x equals 0.4 times x1. So that will be 2.05 times 0.4, which will give us 0.82 cubic meters or 820 liters. For the reactor 2, when x2 is equal to 0.8, then FA0 divided by minus RA at 0.2, which is a conversion x equals 0.8, we will have that this relation FA0 divided by minus RA2 is equal to 8 cubic meters, and the volume of the second reactor will be FA0 divided by minus RA2 times x2 minus x1. So the volume 2 will be 8 times 0.8 minus 0.4, which will give us 3,200 liters or 3.2 cubic meters. So, to achieve the same overall conversion, the total volume of two CSTRs in series is less than the required for one CSTR. And we can see it here in this plot. Remember that for only one CSTR, we needed a volume equivalent to the rectangle of 8 times 0.8. Note again that for CSTRs in series, the rate minus RA1 is evaluated at a conversion of 0.4, and the rate of minus RA2 is evaluated at a conversion of 0.8. The total volume for these two reactors in series is the volume equal V1 plus V2 equal to 0.82 cubic meters plus 3.2 cubic meters, which is 4.02 cubic meters or 4,020 liters. By comparison, the volume necessary to achieve 80% conversion in one CSTR is equal to the volume FA0 divided by minus RA1 times x, which is equal to 8 times 0.8, which was 0.64 cubic meters, equal to 6,400 liters. That's what the value that we obtained in the first problem of this section. Note that the sum of the two CSTR reactor volume 4.02 cubic meter in series is less than the volume of one CSTR 6.4 cubic meters to achieve the same conversion. And we can say that we need only minus RA as a function of X and FA0 to size reactor, because that's all what we need to build our Levenspiel plot.